Okay, so I'm going to be talking about fixing balanced knockout tournaments, which is joint work with Harris's Serge Gaspers, Nick Mattei, Paul Stursberg, and Toby Walsh. And I'll be presenting this paper at AAAI at the end of the month. So the motivation, so we're interested in balanced knockout tournaments because it's a widely used format in the world of sport competitions. And so, for example, the World Cup or Wimbledon both use balanced knockout tournaments in the final stages of a competition. Balanced knockout tournaments have a few nice properties. So, for example, there's no incentive to lose in knockout tournaments, unlike some other form of tournaments. They're fair, and you can run a great number of matches in parallel. So the setting we're looking at is we're given a tournament graph, which so we have a set of players or teams, and the tournament graph tells us which team beats which, and so this is encoded via the edges, and then we're given a draw, and we can compute the outcome of a balanced knockout tournament using the tournament graph. So, for example, here we have Germany, Brazil, the Netherlands, and Argentina, and we have Germany matched up against Brazil and Argentina matched up against the Netherlands, and so we can use the tournament graph to compute the outcome of a balanced knockout tournament. So we can see that Germany beats Brazil, then Argentina beats Netherlands, and finally Argentina beats Germany. So Argentina wins the tournament when we have this draw. So clearly, the outcome of the tournament is dependent on the draw. So, for example, using the same previous tournament graph, we can have a second seeding, the one on the right here, where we've swapped the Netherlands and Brazil in the draw, and so Germany now beats the Netherlands, but then Argentina is beaten by Brazil, so the finalists are Germany and Brazil, and Germany beats Brazil. So Germany, if we want Germany to win the tournament, the draw on the right is the correct one. So the problem we want to study is the tournament fixing problem. So we're given n agents, a tournament graph on n, and a distinguished agent I, and we're asked if there exists a draw such that I wins the balanced knockout tournament. So this is a restricted version of more general problems which have been studied in the past, and so more general problems include probabilistic version of that, where instead of being given a tournament graph, you're given a probability matrix between, like which encodes the probability which of a team beating another, and you're asked, is it possible to find a draw with such that I wins with more than probability, whatever, and or you can think about the problem where tournaments, where you have a graph structure where, or it's not a binary tree, it could be some other tree structure for the tournament. So many restrictions and subproblems have been solved. Hardness has been proved for more general versions of a problem. It was first introduced by Wu and Shoam. The TFP has been mentioned repeatedly in the literature on tournaments. So we have by Lang and Vasilevska Williams a fair number of times. And it was also mentioned as an interesting open problem in Richard Lipton's blog in 2010. So the main result of our paper is we show that TFP is NP complete, and this hardness result actually implies many of the hardness results which have been shown in previous papers, because we're looking at a more restricted instance of a problem. And it also has a few nice corollaries. So, for example, we can say that because of the hardness of TFP, there's no polynomial time algorithm for probabilistic version of a problem approximating the maximum winning probability within any given factor. We can also extend this reduction to show that even if a player is a king, the problem is still hard. So kings were a property of players that was studied a fair amount by Vasilevska Virginia Vescoso-Williams, where effectively a player I is a king if for all other players they're either beaten by I or beaten by another player which is beaten by I. And we can show that even if the distinguished player is a king, then it's still NP hard to find a draw where that player wins, in the worst case. And we also show polynomial algorithm for restricted cases, which I'm going to talk about later. So the reduction itself, we reduce from a variant of 3 sat where each literal can only appear twice in the clauses. It's a fairly large reduction, which has quite a big constant, so it's unlikely to actually be of much relevance in practical or in tournaments in the real world, but it's still of interest because many researchers have been actively looking for a polynomial time algorithm, and so this shows that it's very unlikely that they'll find one. So the high-level structure of the reduction uses something which we've called the spawning process. So we basically generate the tournament graph between players which will be finalists in the balanced knockout tournament using this spawning process. So the way to read this diagram is so basically, unless specified otherwise by an edge, a player to the right always beat a player to the left. And so the spawning process we're generating new players step by step. So at step 0 here, we're starting with player I, and at step 1, we've generated another player which player I beats. And we do the same thing at step 2 and then at step 3, and we end up with this structure. So what's useful about this structure is it basically heavily constrains the draws in which I can win. So basically I can only win the tournament, has exactly the right number of players to win the tournament. Or we're basically making sure that a fair number of players have to be in certain positions. And this allows us to encode gadgets as sub-tournaments. I'm now going to describe the gadget. So this is the choice gadget, and so the way to read this again, right, unless specified otherwise, players to the right beat players to the left, and players at the top beat players at the bottom. So basically this gadget encodes a sub-tournament where you only have 2 possible configurations, and depending on which configuration you choose, you end up with a set of other players which are available to place in other sub-tournaments. So this corresponds to a literal in the SAT formula, the choice, a variable, and depending on which sub-tournament we choose, it's basically an assignment of that variable. We also have clause gadgets, which encode a sub-tournament which needs a certain player to be available for a given player MJ to proceed to the 4th round. And because of the spawning process, that player MJ needs to be in the 4th round. So based on the choices we made using the choice gadgets, different players will be available for the clause gadgets, and if the formula is unsatisfiable, we won't have enough players available for clause gadgets, which means the MJ players won't be available in the 4th round, and the final player won't be able to win. The player I won't be able to win. That was the reduction. We also look at the case where you have a constant number of player types, and so by constant number of player types, I mean that you can partition the set N, or the set excluding I of agents into a number of sets such that each agent in the set has the same relation to agents outside the set as other agents in the set. So and so we show that the TFP problem can be solved in polynomial time if you have a constant number of player types. We use dynamic programming to do so. It's also possible to use this algorithm to count the actual number of draws instead of just looking for one. And only it takes nk time, where k is the number of player types, and we were unable to show that there's a FPT algorithm to solve this problem. And yeah, we weren't able to show W1 hardness reduction. Inspired from the polynomial time algorithm, we also have an exponential time algorithm, which basically can solve the general problem in time 2.8285 to the n, and using space 1.7548 to the n. And there's actually a whole family of these algorithms depending on what space-time trade-off you want. So the table shows the different values. So in conclusion, although changing the draws is not always a realistic scenario, it's actually useful to be able to compute all these things in post-analysis of tournament draws. It also sheds light on the relative strength of the players, and I think the research can be extended. Some of the future directions would be to look at parameterized algorithms for the problem, or specifically solve the one for a constant number of player types, see if we can find an FPT algorithm, and look at related parameters. Okay, thanks.
You have the mic, so just ask the questions.
Sorry?
Questions.
Yeah, questions?
Do you guys have any questions?
You mentioned that it's NP complete.
Mm-hmm.
You said mentioned that it's NP complete to find the result, right?
Can you hear him?
Yeah. How bad is NP complete for example, a FIFA World Cup match to predict?
Oh, well, as I said, it's unlikely to actually.
Is it realistic to?
No, the reduction, like this, the effect of reduction would only sort of take place in huge tournaments. So it's really interesting from a theoretical point of view because it just shows you won't be able to find a polynomial time algorithm, basically. So in practice, I think you can, like there's heuristics and that you can use to find seedings or draws relatively easily, I think. Yeah.
So in practice, it's possible to do even if it's not NP. It's still NP complete and not polynomial time, right?
Yeah. Well, I mean, yeah. So.
Any questions from your side? Okay. Thank you.
Thank you.